So Lagrange multipliers is a way, it's a method to find the maximum or minimum value of a function subject to a constraint. Okay, so this is this kind of idea is actually very important. I've seen papers involving economics, for instance, that deal with the Lagrange multipliers. Let me go to a little picture here. Well, let me just do, I'll read the highlighted part. That's why I highlighted it, okay? So we want to try to find extreme values of a function, and let's say it's a function of x and y, but this could be extended to a function of 3 variables. But let's say we want to find extreme values of a function subject to a constraint of the form g of x, y equals k. So when you set a function equal to a constant, that is a constraint. You're requiring the function g to equal k. So we seek extreme values of a function f of xy when a point xy is restricted to lie on the constraint curve, the level curve g xy equals k. Okay, so in the figure 1, and I'll show it to you, they're going to show level curves of the function where f of xy equals c, where c equals 7, 8, 9, 10, 11. Okay, and let me just go right to the picture here. I think we can show that picture now. Okay, so you have these different level curves of the surface, and that's those red curves there in figure 1. Now what we're doing is we want to find the maximum values of, well, we want to see where the function is maximized, but we want it to be maximized subject to a constraint. So the constraint is that g of xy equals k. So that g of xy equals k curve is graphed in 2-dimensional space, and all the xy coordinates on the blue curve are coordinates that when you substitute those coordinates in the function g, you're going to get k. So for instance, what we want to know the highest value of the function f subject to the constraint. What would the highest value of the function x subject to the constraint be? That's right, Ellie, 10. So indeed, you see, when like the dot there, the blue dot on that blue curve, the constraint curve, is the value that, I mean, again, all the points on the blue curve, all the xy coordinates on that blue curve satisfy the constraint. But the xy coordinate, the blue dot, is the xy coordinate such that the constraint satisfied, but the function equals 10, which is the highest value. You see that? All right, are there any questions on that? Well, we want to find the xy coordinates such that the function's maximized. Okay, and they comment here. They comment, and maybe I'll put this in pink. Well, I didn't want it all in pink. Hold on. Let me unhighlight it. Okay, so to maximize the function subject to constraint, Well, we've seen what that is. But it appeared the maximum value of the function subject to the constraint is equal to 10. But it appears from figure 1 that this happens when these curves just touch each other. In other words, when they have a common tangent line. This means that the normal lines to the point x sub 0, y sub 0 where they touch are identical, and so the gradient vectors are parallel. Okay, so do you see this in the picture? Okay, let me see if maybe I can go to the whiteboard and show it to you clearly what they mean here. All right, go to the whiteboard and let me get my stylus out here. Okay, so from figure 1, section 11.8, okay, this is the curve, level curve of the function f, and that level curve is all of these coordinates here on the level curve, all those xy coordinates. And actually, maybe I'll hold on here. It's worth drawing an x and a y-axis. Okay, so all these points here, okay, all of these x, y coordinates on that level curve, well, the function evaluated at all those coordinates equals 10. Now, this constraint curve comes over here like this, right? So this is your constraint, some constraint g of xy equals k. And this point right here, this coordinate xy is the coordinate. Okay, let me just get this off here. That coordinate xy is the coordinate that satisfies the constraint but also maximizes the function. And remember, we said that the gradient vectors, let me see here. Yeah, gradient vectors to level curves are perpendicular to the level curve. Okay, so this here, this is the gradient function. And actually, hold on, let me be even a little more clear. Let me call this point x sub 0, y sub 0. So the gradient vector of the function f would be, well, hold on, let me do one more thing here. Hold on. So I'm drawing a tangent line to the function f at the point x sub 0, y sub 0. Well, I'm drawing a tangent line to the level curve, f of xy equals 10, at the point x sub 0, y sub 0. It should be clear that the gradient function, okay, the gradient of our function at x sub 0, y sub 0 is perpendicular to that green tangent line. And it makes sense because we learned that the gradient vectors are perpendicular to level curves. So of course this gradient vector is perpendicular to that red level curve. But what is this constraint here, g of xy equals k? What is that constraint? Well, so maybe I'll just, yeah, that's our constraint. That constraint itself is a level curve, right? So I could draw, if I were to draw the gradient vector of g at the point x sub 0, y sub 0, maybe that gradient vector goes this direction. Okay, that could be, for instance, the gradient of g evaluated at x sub 0, y sub 0. Okay. Now the gradient of g could also point, you know, in the same direction as the gradient vector of f. I just drew the gradient as opposite of the gradient. The gradient of g is opposite the gradient of f, but I just drew it that way. But the gradient vector of g could point in the same direction as the gradient vector of f. Okay. But keep in mind that the gradient vector is also perpendicular to that tangent line. So this means then, that we can relate the gradient function at x sub 0, y sub 0 to the gradient function, I'm sorry, the gradient function of f at x sub 0, y sub 0 is related to the gradient function of g at x sub 0, y sub 0. Right? How are they related? What am I looking for here? How are they related, class? This vector and this vector are it begins with a P, then an A, then an R. The vectors are parallel, right? That's right, Ellie. I mean, the vectors go in opposite directions, or they could go in the same direction, but they are parallel. So this means then that I can come up with an equation that relates the gradient vector of the function f to the gradient vector of the function g. The gradient, since those two gradient vectors are parallel, this means then that the gradient vector of f is equal to some lambda, some scalar multiple of the gradient of g. And from this, this symbol here, this symbol lambda, is what's called a Lagrange multiplier. We call that a Lagrange multiplier. Okay. Are there any questions on this? Okay, well, let me get back to the book then. So this idea can be also used for functions of 3 variables. Okay, functions of 3 variables. So what I'd like to do is I'd like to do a problem with you here. Okay, let's do a problem. An applied problem. Okay, so let me give you a moment to copy this example down, and then we'll go over this problem. Okay. Okay. While you're doing that, I'm going to draw another little picture. Is this point, by the way, is this point 1, 0, negative 2, is that point on the plane? The answer, of course, is no. But, and how do you know that, by the way? That's right, Ellie. How do you know that? How do you know the point 1, 0, negative 2 is? That's right. If you plug in the point 1, 0, negative 2 into the equation of the plane, the equation of the plane is not satisfied. Okay, so 1, 0, negative 2 is, say, out here, 1, 0, negative 2. Now, do we agree, would there be a minimum distance from a point to that plane? Does that minimum distance exist? That's right, Charles. It does exist. And in fact, would it be unique? If you have a point and a plane, yeah, it would absolutely be unique, right? That's right. Good, Charles. That's good. It's kind of like the movie The Martian. Remember when, what's his name? That guy who was the movie The Martian, the guy who played the Martian on Mars. He was trapped and he had to get rescued. Gordon says, who? Mark, I forget his name.
I think it is Mark Watney.
Mark Watney. I thought it was Matt. I think it's Matt Damon.
Well, that is the actor. The character is Mark Watney, I think. Right?
Oh, I gotcha. All right, you're right. So Mark Watney, played by Matt Damon, he has to, jet up into the spacecraft returns for him, and he has to pick the right time, right, to get to the spacecraft, shortest distance kind of thing. All right, so, okay, well, here's the thing. What function are we trying to maximize or minimize? We're trying to maximize or minimize a distance function. So we got it. The distance function is our function f. What's the constraint? Well, the constraint is that the point. Well, let me phrase it the right way. The constraint is that whatever this coordinate is, okay, on the plane, it's on the plane. So minimum distance, I know one of the points is 1, 0, negative 2. The other point, I don't know yet, but I know that that point, whatever it is, whatever that x, y, z point is, I know that it's on the plane. Okay, so that's my constraint. Now let's go ahead and get to the solution here. Okay, so the function that we're going to minimize is the distance function. We know one of the points is 1, 0, negative 2, and the other point, x, y, z, is on the plane. So this is the distance function between a point, x, y, z, and a point 1, 0, negative 2. Okay, let me give you a moment to catch up here. Okay, so this distance function, I could call it my f of xy function. But the problem is, I don't want to do that. I don't want to do that. I don't want to call it that because the distance function has a square root in it. Let me define my function f of xy, or actually, sorry, it's f of xyz, right? Let me define that function as the square of the distance. If I can find the coordinate x, y, z that minimizes the square of the distance, then that also will equivalently minimize the distance. And so it's easier to work with the square of the distance because there's no square root involved. So we've established what our function of x, y, z is. Now we wish to minimize that function subject to the constraint. The constraint is that x plus 2y plus z equals 4. So g of x, y, z equals 4. Okay, let me take my email off. I don't want any distractions here. Okay, let me know when we're ready to go to the next page. Please let me know if there are any questions. We're looking for this coordinate, x, y, z coordinate. So what we're going to do, right, is the following. We're going to find the gradient of our function x, y, z, and we're going to set it equal to some lambda. Lambda is the Lagrange multiplier. We're going to set it equal to lambda times the gradient of g of x, y, z. So we have to find the gradients of our two functions f and g. So far, are we good? Are there any questions? Okay, may I go to the next page? Give me a thumbs up if you're good. Okay, Charles is good, Juliana's good, Ellie's good. Okay, well let us proceed then. Now we find the gradients of both of these of both of these functions. And we wish to find x, y, z such that the gradient of f equals lambda times the gradient of g. And so what I have to do is I have to set up my equations. Now let me ask you, how many unknowns are we dealing with when we have this gradient of f equals lambda times the gradient of g? How many variables are there? I mean, what are our variables that we're dealing with? We have x, we have y, we have z. Is there anything else? X, Y, Z, but also it's not a variable, but there's a lambda too, right? There's a lambda also. Okay, so if we set the gradient of f equal to lambda times the gradient of g, these are going to be the three equations that we get. But then there's the constraint equation. You see, we have four like parameters, well, four variables, three variables, x, y, and z, and then this other Lagrange multiplier lambda. But that's like four unknowns. To deal with four unknowns, we need four equations. And now we have four equations. The trick is now, what are we going to do? What are we going to do? So this might seem a little strange to you, but it's really like solving a system of equations, a system of four equations with four unknowns. So what we can do is we can solve for x, y, and z in terms of lambda. And you notice what I do is every equation I put like a number by it, because it'll help me follow the work. And I want you to do that too. You know, like for problems on your next exam, exam 2, I want you to label your equations, because it'll help you and it'll help me when I look at the work. You know, it just and especially it'll help you. It'll help you follow what you're doing. Okay, so now we're not done yet, of course, but are there any questions so far up to like this page? Okay, so what do you think we're going to do? So what equation have, I mean, I have these three interesting equations where x, y, and z are functions of lambda. And what equation, you know, I used equations 1, 2, and 3 to get these equations. Equations 5, 6, and 7. What equation has not been used yet? What equation above has not been used yet? Equation 4. That's right, Ellie. What should I do with equations 5, 6, and 7 here? What should I do with them in regards to the constraint equation 4? Substitute them in, excellent, Ian. That's what we're going to do. Okay, so let me know when you're ready, and I'll go to the next page and show you this. Okay, maybe give me a thumbs up then when you're ready. Okay, thank you, Ian. Thank you, Ellie. Thank you, Charles, Juliana. Thank you, Madeline. All right, I think hopefully everybody's good. We're going to substitute in now the x, the y, and the z in the constraint equation, and this allows us to solve for lambda. We will get lambda equals 5/3. And now what we can do is we can take lambda equals 5/3 and substitute them back in equations 5, 6, and 7, thereby getting our x, y, and z values. Absolutely amazing. Absolutely amazing. See, you can rescue Matt Damon from Mars now, right? But you can understand that this is a or Mark Wazowski, but you can see that this is a pretty good application, a pretty important application. Finding minimum distance is important. If you're, shooting a rocket somewhere and you want to hit a plane in a certain point, minimum distance, you want to. If you just want to hit the plane, you want to hit it in where the distance is minimum, because that's less fuel, right? So, so the coordinate is 11/6, 5/3, and -7/6. And if you plug that coordinate back in the distance formula and work it out, I know you can do this. You don't need me to do this for you. Just if you substitute in, hold on here. I don't know why that's not acting like it should. Yeah, if you substitute, I don't know why that's not working. Hold on. Yeah, if you substitute in the coordinate, this coordinate, into that distance formula and work out the math, the exact distance, and WebAssign will want the exact distance, it'll be 5√6/6. If you simplify like the square root, WebAssign would take the square root, not in simplified radical form, I believe, but in simplified radical form, this is your distance. Okay, let's copy that. Are there any questions on this particular problem? It's kind of like, in a sense, how many think, gee, seems a little strange, this kind of problem, a little bit like I've never done this before, how many are thinking this is kind of, interesting, maybe how many of you kind of feel that way? It's pretty cool. I agree with Ellie, and it's interesting, and it's an important application of calculus. The book has an example too. I would recommend you look at example 2 in the book. There's an example 2 and an example 4 in the book that are nice to look at. And then Lagrange multipliers, they even have, they show how to do, how to maximize or minimize a function subject to even 2 constraints. But we're going to keep things simple for right now. Are there any questions? Okay, I'll stop the recording.